Hello, everyone. Today, we are presenting our paper, Robotic Concrete 3D Printing, Continuous Toolpath Planning, from Single Curve to Voxel-Based Systems for Design to Production of Urban Furnitures. I'm Mostafavi, Associate Professor at Texas Tech University and the Director of hi-darslab at Huckabee College of Architecture, together with my co-authors Edgar Montejano, Bagheri, Ali Etemadi, Cole Howell, and Dr. Asman Mehan. We are glad to be part of this session at ARCC 2024 conference in Aarhus.
The background presented in the paper discusses various projects addressing toolpath planning in concrete 3D printing. We have addressed challenges of continuous printing and have discussed how researchers are developing integrated computational design and fabrication-aware methods to overcome challenges of 3D printing complex structures using concrete. Our approach aligns with recent research on data-driven 3D printing strategies, including performance-based generative design, digital fabrication, and bio-inspired architectural design. Our work explores advanced toolpath-based design and assembly methodologies in additive manufacturing and digital prototyping for architectural applications. While most data-driven methods such as finite element analysis and topology optimization are based on discrete systems, 3D printing often requires continuous toolpath planning, which then requires translating discrete geometry into continuous path. This paper categorizes 3D printing efforts to provide a comprehensive approach for continuous toolpath planning.
Our focus is divided into two separate yet complementary approaches, each explored for both pedagogical reasons and research goals across the span of a year. Our curved-based approach was developed during the autumn of 2022 and explored through the means of AI-generated porosity systems, reaction diffusion, and other computational techniques. During the spring of 2023, we pursued a voxel-based method to execute the pedestals for Fabricity XR, which were on display during the Venice Biennale later that year. The technique focused on tetrahedron octahedron cells and involved structural analysis to optimize the form as well as the toolpath design. The first three sets of projects presented here are the results of research and design done as part of a graduate level technology course in autumn 2022. Starting with the first, the project employs generative AI to create sets of porous images and develops a system to translate 2D images representing porous facades into 2.5D cellular systems for continuous 3D printing. The process begins with prompting generative AI to generate 2D images of porous cellular structures, which are translated algorithmically into continuous 3D toolpaths with variable heights. In the prototypes component, the primary design goal is to create structures that integrate seating elements into walls characterized by unique patterns and varying degrees of porosity. Generative AI using the Midjourney platform with specific prompts such as porosity, canopy, biomechanical, bench, wall, and organic produces a series of images that serve as the foundation for subsequent stages. Shown here is a close-up of the 3D printed one-to-one prototype as part of the porous wall. The AI-generated printable porosity is showcased with the left images providing a top view and the right image showing a side view with the varied heights of 3 layers, produced with a continuous toolpath.
The next project addresses the assembly of aggregation of concrete 3D printed components to build something that could be expanded later. The stacked wall project initially introduces a system where multiple components stack, creating a Tetris-like structure integrating niches of varying sizes and depths inspired by urban context adjacent to an architectural site, addressing key challenges in 3D printing, particularly in assembly processes. The project aims to merge the wooden shelter concept with traditional adobe house inside walls, focusing on combining walls with shading. This initial design merges the concept of a wooden shelter with traditional adobe house inside walls, focusing on combining walls with shading. The one-to-one prototype comprises 3 components with L and V typologies systematically stacked. In this slide, You can see the toolpath design strategy that creates continuous cavities within each component and develops a continuous printing path for the outer boundary connected to internal niche. The left image shows two-component prototype featuring extruded curves with internal niche, slightly tapered towards the front flat outer surfaces. The right image gives a close view of the Tetris-like interlocking configuration. Despite the fragility of the straight outer boundaries, the internal cavities enhance the overall stiffness.
The third method we use, in the third method we have used reaction diffusion to design a concrete printed bench. This model was chosen to generate internal and external performative tectonics, which enhance the structural robustness of the 3D printed surface. Apart from the complex appearance of the pattern, the geometry contributes significantly to the mechanical stability of the structure. One of the key features of this model is its internal porosity, which aligns with the natural forms and functions. The toolpath planning system optimizes for single or double curvature surfaces, with double curvatures providing structural stability. The prototype bench, which fits within a 40 by 40 by 80 centimeter bounding box, incorporate fractal tectonics and double curve properties to minimize material consumption and enhance efficiency. These two photos are actually showing the prototype exhibited as part of the last year ARCC conference in Dallas, hosted by Texas Tech University.
Moving toward the second category of toolpath planning, here we present design and production of pedestal systems using voxel-based approach in toolpath design. In this project, we explore voxelization, which is fundamental to our approach in robotic concrete 3D printing. Voxelization translates complex geometrical data into a grid of 3D pixels or voxels. This method received any closed 3D geometry and translated into voxel-based output for continuous 3D printing. We employ a tetrahedral, octahedral honeycomb tessellation for voxelization. This choice is deliberate, as it guarantees both the printability and stability of the structure by maintaining optimal angles and throughout the printing process. The geometric configuration supports continuous toolpath planning, which is essential for seamless and robust construction. Computationally, recursive voxelization adds another layer of complexity and robustness to our design. By recursively subdividing each voxel into smaller units, we can potentially reinforce areas that are structurally vulnerable. This recursive approach ensures that stress is distributed more evenly across the structure, reducing the likelihood of failure during and after the printing process. Each voxel subdivision is calculated to maintain optimal angles and connections, preserving the structural integrity while allowing for greater design flexibility. For lightweight pieces, ideal for exhibition purposes, we utilize a single-layer 3D printing toolpath. This approach leverages the same voxel grid to create structures that are efficient in material usage and easier to produce, making them perfect for applications where weight is a critical factor. The recursive subdivision of voxels adds another additional layer of reinforcement where necessary. This approach not only strengthens the overall structure, but also minimizes the risk of buckling during and after the printing process. By leveraging the advanced voxelization technique, we achieve a harmonious balance between aesthetic quality and structural performance, paving the way for innovative architectural solutions. Our voxel-based system allows for detailed customization. Each voxel can be individually analyzed and adjusted, enabling us to optimize material distribution and structural integrity dynamically. This flexibility is particularly beneficial for enhancing the durability of printed components, as it allows us to reinforce areas prone to stress while conserving material in less critical regions.
prototype the proposed concrete forms and to have a backup in case of failure during transit, we printed 2 of the pedestals in-house using a Big Rep 1 and PLA. PLA pedestals helped inform us of design considerations as we move forward. The prototype was 1-to-1 with the concrete version, consisted of a single toolpath, and was a shell lacking an infill. Results of the prints helped predicate the design despite the sheer slopes of the pedestal walls. The first print was structurally unstable due to using a single wall layer, but this was solved after doubling the layers, which better emulated the print thickness of the concrete.
As a voxelated system, we considered the possibility of breaking these pedestals down into substructures through recursive means, allowing one to turn any tetrahedron, octahedron voxelization into a printable object. These double layer prints, while allowing for larger projects to be realized, could also be applied to our use case to introduce lateral and shear support through the print. While developed, we have not yet printed any objects using the double layer system. We hope to realize the method in the coming semesters as part of the ongoing research efforts. For applications requiring greater structural stability, we employ a double layered fortified continuous toolpath. This method also uses the same voxel grid, but results in a more robust and heavier structure. The additional layer provides enhanced durability, making it suitable for functional pieces that need to withstand higher loads and environmental stresses.
To conclude, this paper explores a series of case studies and pilot projects focused on continuous toolpath planning using robotic concrete 3D printing. It investigates the transition from single curve methodologies to voxel-based systems for designing and producing urban furnitures. The study begins with an analysis and categorization of curve-based continuous 3D printing, highlighting case studies that use AI-driven generative systems, reaction diffusion algorithms, and multi-component assembly strategies with continuous toolpaths. It also explores voxel-based approaches, integrating external surface tectonics and internal infill. These projects demonstrate the impact of creative toolpath planning, showing adaptability in design for specific contexts and functional requirements. They also develop strategies for implementing performance-driven tectonics that enhance structural stability during and after printing. Future research will further develop voxel-based toolpath planning, promising greater flexibility in design and structural integrity in producing building elements and components. This work highlights the potential of computational techniques in systematic and creative toolpath planning to transform architectural design and construction through robotic concrete 3D printing. The projects featured here are the result of collaborative efforts within Texas Tech University and as well as external partners. This slide provides an overview of 4 projects highlighting the contributions of individuals, firms, and institutions to our research. We acknowledge their support, and we are thankful to everyone for their contributions. Thank you for your time and attention. For more information about the projects and related publications, please visit our website, hi-darslab.org, which is also accessible by scanning the QR code presented here. Thank you.
Thank you.